Much for being here for the third and unfortunately last day of this nice event. And today we start with a talk from Hamed Yazdampana on foundational models from time series analysis, foundations, methods, and open challenges.
Hello, everyone. First, thank you for your participation at my talk. Today, I want to present a high-level introduction about foundation models for time series analysis regarding the foundations, the methods, and the open challenges in this topic. In fact, I worked on foundation models sometimes. I joined University of Sao Paulo this year. Before university, I was working in the industry for several years. I worked in AWS at the GenAI Innovation Center, for working on foundation models, attending AWS clients in the Latin America. So I want to present you about the foundation models. It's a new topic. There isn't too much mathematics behind this with the emergence of ChatGPT in 2023. So it became a hot topic, foundation models. And particularly, foundation models for time series is even newer. The last 2 years, since 2024, it appeared in the literature. So the most of the progress on this topic is empirical. There isn't too much theory yet. So what's the motivation of presenting this to you? To talk about the open problems, so challenges that theory and statistics can contribute to this topic. So first, here is the agenda of the talk. First, I will show you the evolution of time series learning. Then I talk about foundation models, the definitions, and the methodology. Then I talk about what is the behind this time series foundation model, which is representation learning and transfer learning. Next, I will talk about some challenges, particularly generalization, uncertainty, non-stationarity, and evaluation of these models. And finally, I close my talk with the open problems. So here, I'm not presenting my paper or one or two papers. It's a general introduction, high-level introduction. It's not a particular paper, so there isn't too much mathematics and formula in this presentation. So we know that time series is ubiquitous in our daily life in different application sectors like energy, finance, weather forecast, health. And when we talk about time series, the first comes to our mind is like univariate signals. There are some collection from the signal during the time, but not necessarily is univariate. It can be multivariate. It can be a special time series like weather stations, so they are distributed in the space and measurement of them during time. It can be trajectory time series like vehicle, animals, or even human using wearable sensors and during some time and in the space, in the trajectory, the data are collected. Or it can be event time series, like, for example, transaction logs. You receive a transaction, analyze it, then approve or reject. If it's approved, then the payment is settled. So it's an event time series. Also, when we talk about time series, most of the people thinking about forecasting, but it's not the unique task for forecasting. It's the most common one, but it can be retrieval similarity, clusterization, classification. In the industry, there are too much application regarding anomaly detection in time series, and it can be imputation of missing values in time series. So different tasks can be applied in time series. About the evolution of time series learning, the traditional one is the local models. In local models, for each series, time series, we have one model. There is a a statistical theory behind that, and the source of the knowledge is the history of the time series to forecast the future. Then, as the progress, we have global models. In global models, we have a set of time series that they share temporal dynamics, and one model is trained for all of them. And the next one is the foundation model, which is trained on the massive heterogeneous data set on, from different domains. And the target of this model can be various tasks, clusterization, classification, and so on. And the evolution is not from a small to large model. It's from forecasting to representation learning and transfer learning. So the objective of foundation model is learn representations. To give more details about local models, so we believe that each time series deserves to have its own model. So for each series, we have one model. There is a strong statistical assumptions for these kind of models, like non-stationarity or stationarity, linearity. They are interpretable, but the issue is that the transferability. If you train the model for a single time series, you want to apply in another time series, even in the same domain, you cannot apply that. You have to train a new model. So the learned knowledge is not transferable using local models. Then we have global models. So for different data sets, we have a single model. For example, in a wind farm, we have different turbines. Each of them have their time series. They share the same temporal dynamics. We trained one model on all of them. The advantage is that we saw it improved the accuracy and scalability. We lose interpretability using global models, but still limitation about transferring knowledge continues. For example, we can learn a global model on electricity time series, like wind power forecasting. Then we cannot apply to medical time series, or even from the same domain. For example, wind power forecasting in Europe, then we cannot use that model for wind power forecasting in South America. What we have to do, we have to retraining or fine-tuning and maybe change the architecture and do everything from the scratch. So the problem of transferability continues in this type of models. But in foundation models, in the training data set, we have heterogeneous time series from different domains like energy, traffic, finance, and so on. We pertain a model, and the objective is not only forecasting, can be different downstream task. So the objective is to learn transferable representations, like latent variables that can serve different tasks. So to summarize talk so far, from local models to global models, so the evolution is on the direction of the forecasting, but for foundation models, the evolution is not from forecasting or small models to large models. It's from forecasting to representation and transfer learning. So it's another type of models. And it can be, the inference can be through zero-shot learning, few-shot learning, or these models can provide uncertainty estimations. It can be point estimation. So as a formal definition for foundation models, we want to learn a function f that map the raw observations to a transferable representation space, which is z. So the target is not finding a function that map x to the final target. So we learn representations, latent variables. Then we add another head, which can be a simple model, use the representations, transfer them for the downstream task. I want to call your attention, foundation is not transfer. transfer is a dominant architecture, but foundation doesn't mean that your model is a transformer. Foundation, it doesn't mean that your model is large. You can have a global model larger than foundation models, but it's not foundation model. So for having a foundation model, you should have representation learning. Then transfer those representations for the downstream task. And it should support various tasks: forecasting, classification, anomaly detection, because you can use representation for any downstream tasks. What is learned using a foundation model? So we are learning like grammar of time series. What is the grammar of time series? What I mean by this, you in your latent variables, you learn trends, seasonality, periodicity. So the grammar of the time series language. You learn the hidden representations that are shared in your temporal dynamics of per-training data set. How it's possible is by the combination of these three blocks. Per-training, that use the heterogeneous large data set from different domains, and use self-supervised learning to per-train your model on this data set. Then in representation learning, you are capturing the temporal patterns in your data set to generate latent variables in the latent space. Representation are generated here. Then you use transfer learning to transfer the representations to the downstream task. Each of these blocks existed in the literature before foundation models. So we had per-training, we had representation, we had transfer learning, but when combined these three blocks, we have the foundation model in the intersection. So these blocks are not new, but combination of them is new that generate foundation models. What is the difference of time series foundation models from large language models? That's another type of foundation models. So time series data are more heterogeneous, because in large language models, you have a natural language. And the natural language analyzing is easier because cat is a cat, dog is a dog, so you can generate tokenization. But in time series, you have frequency that can be minutely, daily, yearly. You have different scales, so the amplitude of your time series can be from each observation from 1 digit to 6, 4, 8, or more digits. The lengths of the time series are different, varies from one time series to another one significantly. You can have univariate, multivariate, so the dimension is changing, and different domains, weather, energy. So the heterogeneity in time series is larger than large language models. So I presented a general definition of foundation model and the evolution of time series learning. Now I want to talk about the methodology used in time series foundation models. As I said, the dominant architecture is transformer. Why we use transformer in time series foundation models? Because they can model a large, long-range dependency. They can capture relationships between observations from different regions of the time series. They can capture the context that which part of the history are contributing to the future. And another property of transformer that they can be parallelized, different from the recurrent neural networks, that parallelization is not easy, but in transformers, we can parallelize the learning process. So scaling is more feasible using transformers. But transformers are not a unique architecture. For example, in TimesNet, they are using CNN. In Tiny Time Mixer, they're using MLP mixer style architecture. But most of them using transformer like encoder, decoder, encoder only, or even LLM model. Regarding how input the data to the model, there are two approaches, one patch-based, another is non-patch-based. So patch-based is like tokenization in time series foundation model compared to large language models. So we can segment the time series in different patches. They can be overlapping or non-overlapping patches, then input them to the model. What's the advantage? The computational cost reduced significantly, because if you use all samples of the data time series, for example, it has 1,000 samples, then your attention matrix has dimension 1,000 by 1,000. But when you generate patches with size like 50 samples, so your attention matrix is 50 by 50. Computation reduced significantly. It can capture a local temporal resolution, but it has disadvantage. So fine-grained information are lost when you use patch-based. In non-patch-based, each single observation input to the model directly. So you preserve fine-grained information, but the computational cost increase significantly. There are different models in the market that they use patch-based or non-patch-based. Regarding the objective function, there are models, most of the models in the market using mean squared error that generate point estimation. There are some models using robust objective function or moment of expert. There are models that are generating predictive distribution using probabilistic objective function like negative log likelihood, and some other models that are using token prediction objective, predicting the following tokens like Chronos or LLM time. Regarding the number of input variables, it can be univariate and multivariate. Univariate, so receive one channel of the time series, but in multivariate, receive all channels together. But the point that many models in the market declare that they are multivariate, but they are not multivariate, because they are receiving all variables of the time series, but they are analyzing each of them independently. So it doesn't capture the joint information, joint distribution from all variables. So they should be considered this multivariate model analyzing all of the variables together, or not, analyze them independently. So regarding the output, it can be a point estimation or probabilistic estimation. There are models that quantify uncertainty in the output, generating predicted intervals or predictive distributions, like these examples, or these models that are generating point estimation. So in this table, I'm summarizing different time series in each category regarding, for example, architecture, regarding the multivariate, but multivariate, as I said, we have to take care. Not all of them are multivariate. Regarding the size of the parameters, we have a small time series foundation models like tiny time mixer with 1 million parameters, and some large like LLM time 70 billion parameters. Regarding the data set size, tiny time mixer 1 billion, and there are models like time GPT 100 billion observations. Patch-based, non-patch-based, regarding the loss function that they are using, and how is the output, probabilistic or non-probabilistic point estimation. So now I want to talk what these models are learning. As I said earlier, the central idea is to learn a function that map raw observations to latent representation space, which is Z. Then these latent representations can be transferred to downstream task by adding some head on top of the model. And why we believe that learning representations is better than learn one model for each of the tasks, because we believe that different domains share same temporal dynamics. So we can take advantage of this shared temporal dynamics to have a single model that generates representations, then transfer them to the downstream task. So it improves the scalability, and it can improve the performance because taking advantage of different domains to learn the grammar of time series. And how or what's the geometry of the representation space? Here I'm showing in 2D dimension to give only the intuition, but it can be embedding a space can have a dimension of 500 or 1000. Can be really, it's really high dimensional space. But the idea is like this. We want to separate representations in the space so that similar characteristics are separated in different spaces of the different locations in the embedding space, like seasonals, trends, so different characteristics are located in different regions of the embedding space. And how it can be done, because we don't have labels, we have extremely large heterogeneous data set, no one labeled them. So like other area, we use self-supervised learning. And self-supervised learning can be done with different approaches like masked reconstruction, next step prediction, or contrastive learning. For example, in mask reconstruction, we have the original time series, we mask some regions, then use an encoder to reconstruct the time series, compute the loss, and do the propagation to improve the performance of the quality of the encoder. Or in contrastive learning, what's the idea behind that? We want to separate representations that similar views are close to each other and negative pairs are farther apart. So we have, for example, an anchor, which is the reference time series. Then we generate positives with some techniques, for example, do some augmentation to generate positives. And using info NCE loss function that separate negatives from positives. Negatives are free and other time series from your data set, but for positives, we generate positives, adding some augmentation. But we have to take care, yes, which kind of augmentation, because not all augmentation can generate positives. And the parameter theta, the parameter theta here controls the sensitivity of the loss function to difference of similarity. Theta not tau, the temperature. So here is the full cycle of time series foundation model. We have a data set per training, then we have the model that generates representations, then we have a target data set that using some new head to transfer them. And for transfer learning, there are different techniques. It can be, for example, direct usage using a zero shot to generate the output, or it can be through fine-tuning, fine-tune all parameters or part of the parameters of the time series foundation model. It can be through prompt-based transfer. So we guide the model how to generate the output through prompts, or it can be tokenization based. So the time series is tokenized, then used in the model to generate the output. Why transfer works? As I said, because time series from different domains, they have shared latent spaces. So these shared latent spaces help us to generate, to use transfer learning, that these representations are capturing different characteristics in time series like terrain, seasonality, and so on. So far, I talked about the advantage of time series foundation models, how they are generated. Now I want to talk about their challenges. What are the problems with these kind of models? The challenges can be like generalization, uncertainty estimation, non-stationarity in the time series, and how they should be evaluated. What is the fair evaluation of a time series foundation model? Regarding non-stationarity, it's so common in time series data that average on variance, mean and variance of the time series in the past is different from the future, so it's a challenge in time series foundation model, and this non-stationarity can happen because of concept drift, because of different data collection mechanism. Those sensors are changed, seasonality changed, it can have any reason, and it make forecasting difficult in time series foundation model. It can be, another challenge is a distribution shift. So the distribution of your pertaining data can be very different from the target data. So the shared temporal structure is very small. So the key question is to how far the distribution of your pertaining data set can be from the target data set to guarantee transfer. Another challenge is the uncertainty estimation. The models that claim they generate probabilistic estimation, they generate predicted interval or predicted distribution with some coverage, for example, 90%. But when we apply them in real life, we can see that the coverage is lower, like 60% or even higher, like 99%. But the point that there is miscalibration. So it's not respecting in real life the declared coverage. And we should use some techniques to calibrate the uncertainty. And it's not an easy task in time series because time series are not exchangeable. What I mean by exchangeable, so if you cannot in time series permute the order of observations, which is required for traditional uncertainty quantification. But there are techniques to address this, like using variation of conformal prediction, like block conformal prediction, adaptive conformal prediction to address this, but it's not straightforward using the traditional uncertainty quantification approaches to calibrate the model. And regarding the evaluation, benchmarking in time series foundation model is not easy task like other models. We only generate train test split and guarantee that your test is separated from train data set, because you have extremely huge data set from different domains that they are not well documented. For example, proprietary data set, they don't have organized documentation, they are partially documented, or public data set, they have source, they have the same source, so it's not well documented. When you separate some part of your data set for benchmarking your test set, it can have the same sources of your pertaining data set, can have temporal leakage, near duplicates. So when you are evaluating your foundation model on your benchmark, it's difficult to guarantee that it's really unseen data. Many papers are reporting average benchmark rankings in time series foundation model, but it's not enough to look only at the average performance. Imagine you have two foundation model, a time series foundation model. One of them has a fair performance, but stable in all domains, but the second time series foundation model has a fantastic average benchmark ranking, but in some domains performing fantastic. In some other domains, the performance is catastrophically bad. So you should measure the performance from different perspectives, or even in different domains, different metrics are important. In, for example, energy, they care about the peak of the demand. In finance, they care about tail risk. In medical application, they care more about uncertainty estimation, and reliable predicted intervals. So different domain demand different evaluation, and how to report the performance of your model is not an easy task like traditional deep learning models. So I talk about the challenges, but here is the core of my presentation, because as we saw so far, the progress is empirical. There isn't too much mathematics and theory behind this. So what happened in these 2 years? They added more data, trained the new model, fortunately performance increased. They added more parameters, increased the size of the model, performance increased. Change, adding more domain, the diversity in the data set, performance increased. But they don't know what they have to do to define, because learning this model is not cheap. It costs thousands of dollars. So you cannot empirically do trial and error. So far it's working, but it's missing the theory behind that. And what we can contribute, so my purpose to present this, to encourage mathematicians and statisticians to work on the theory. For example, what we can do about transferability, reliability, adaptation, and scientific understanding. These open problems. So for example, transfer learning, how we can generate a transferable transfer measure. So before training a model, before generating a new time series foundation model, we measure the transferability. What should change in the model? The source of the data must be changed. Which kind of data must be added? The size of the foundation model should be changed. The architecture. So the open problem generate a measure that predict transferability. Having this, then we know what we have to do to generate model. We are not doing another random experience to generate a model. And in my opinion, today, generating a new time series foundation model is not a game changer, because there are different foundation models. What is missing? Theory behind that. What we have to do to generate a new model that guarantees transferability. Or, for example, for uncertainty quantification, there is active research to measure uncertainty on these models. As I said, traditional techniques should be changed to work on these models in time series, and the declared coverage is not respected in real life. So researchers are using conformal prediction, but the variation of that, like adaptive conformal prediction, block conformal prediction, or online calibration to quantify uncertainty in a foundation model. So it's the active line of the research. Another important open problem is the adaptive deployment. So what happened today? We deploy a model, we observe the performance, we see some deterioration, and then decide to generate a new model update or not. So what is missing? Because the deterioration can be observed in different domains, different level. So what is missing? Having a metric, so alert us. Now you have update. You need to update the model, because update is not cheap and it's taking time. You have put like $500,000 to generate a new model. You need a large data set, so and take time. Some models take weeks to be trained. So having a metric that define for you when update is needed, and what is the second phase? What should be updated? Okay, I receive an alert with some function that is defined mathematically that I have to update the model. But what should be updated? Part of the parameters, all of the parameters, your data set, what should be updated and how should be updated. So that's missed in the market and literature. Many companies are investing on these topics, big techs, billions of dollars they are putting on this, and they don't have a theory that support this yet. And the last one that I'm presenting here is about scaling laws. Because in large language models, you have better performance when you increase the number of parameters, you increase the volume of your data set and the computation. You receive a better model in language models, large language models. But in time series, beside these factors, model size, data volume, and compute, you have some other statistical structure about your time series, like diversity, distribution shift existence in your data set, temporal structures. So that's missed in the literature in the market. What factors should be changed that guarantee scaling and transfer? So we want to have a technique to identify the properties of the pre-training data set that guarantee transfer. And it's not only by using more data or increase the size of the model. I'll give you an example here in this slide. So this model, tiny time mixer, has 1 million parameters, 1 billion data points, and it beat the performance of many of these models that have millions of parameters, like 700 millions or 100 billions of samples, and it beat the performance. Is much cheaper compared to others. Still is expensive. They train these tiny time mixers on 6 NVIDIA A100 GPUs. So each of the GPUs cost almost $50,000. So 6 is $100,000. And it's trained in almost 24 hours. So it's cheaper, faster compared to others, and it beat the performance. Why? Because they cared about the data set. They didn't only add more data. They care about this theory that I said. But not cared statistically, by intuition. What I have to add to my data, to my model. So there is room. I don't know the authors, but it's from a paper that presented in NeuroMat, I think 2024. But exactly with this name you can find in the internet, but I don't know the name of the authors. So we see that it's possible. With the smaller models, we beat the performance. What we need, as I said, the theory to guarantee what we want before doing a new experiment that costs too much money. That's it. Thank you.
So thank you very much for this nice talk. Any question?
Thanks for the talk. So I have a quick question. So in the foundation models for tabular data, it seems that like using real data sets to train this model doesn't improve on using like just simulated data. So you train these models on simulated data, and it seems it works even better than if you're using real data. So in time series, do people try to use simulated data instead of real data?
Yes, it's common to generate simulated data. For example, for contrastive learning, when they augment, they generate synthetic data to help separate positives from negatives. Is common.
But are there models that are just trained just on?
Not only simulated data. There is real data from different domains. No. In this case, they're using real data also.
Hi, teacher. We're talking about not optimized vision about time series, like I understand for your presentation, okay? You come from the private sector. You have an experience that this kind of things make is good, and the result is great for a company or something like that.
Making money or because yes, it reduced the cost significantly. So when you use the foundation models, you can automate many tasks, and then you use your human resources in the area that these models cannot solve. So generate a good, great impact by reducing the cost and removing iterative task that doesn't need necessarily be implemented by human. Uh, it has good result. Because of this, there are too much investment. Otherwise, doesn't matter.
Yes, in this point of view, it's a it's a s- it's a sample that this kind of time series is good, is function. There is function in this kind of some kind of model. Yes, is an example. Oh, it's okay. Uh, okay, for now, I remember another question.
Hello, thank you for the presentation. I have a quick question about the part on uncertainty quantification. So I understand that in time series, you lose the hypothesis of exchangeability in the data. It's not exactly IID. But my question is in terms of if the methods change because of the architecture of the model, because if you just lose the hypothesis of exchangeability, then I guess other methods that would work on other time series models that aren't transformer-based time series models would be similar. My question is more in the direction of if that's the case, if the application of uncertainty quantification techniques is similar to other time series models, or if there's some change because of the architecture.
Yes, it can be similar to other time series application, because the problem is not in the model, is in the time series that they are not exchangeable. So if you have a method that can apply to other time series, you can apply also here.
One aspect I was missing from your challenges is irregular time series, right? I ones that are irregularly sampled. And do you know how good these foundation models perform for that, for the irregular sampled time series? Irregular points, like you're in a hospital in medicine, on Monday my blood pressure is measured, on Tuesday it's not, and then on Wednesday it's in the morning, and Friday it's in the evening.
Yes, it's a really good question. And one of the advantage of time series foundation model is that it can work in a regular time series observation collection. For example, in traditional time series analysis, you should create some regularity between them. But in time series, because they can predict different resolutions, daily, yearly, monthly. So with regularity, also they can take care. They can, because they can do various downstream tasks. They do imputation to create regularity, some interpolation, then generate the final output. They show superiority in this aspect compared to traditional time series.
Okay. The way I understand, you want to have a model, a foundation model that can somehow generalize all applications from finance to health, and give a time series, and then it will predict. but how can you identify whether the model actually first classify the thing, this is a health series, and then applies a specific model for this one instead of generalizing everything?
In fact, the model is not recognizing the domain, the sector. It capturing the temporal dynamics. That it doesn't matter if it's from finance, it's from medical application. It captures like in the representation space, latent variables, the trends, seasonality, or resolution, or some other characteristics. Then it can be shared in different domains, medical application, finance, and using those information transfer to your downstream task. So it's not recognize the domain; it recognizes. In my, let me, here also I have characteristic is not. Let me see. So here, okay, there is a trend. I don't know which slide you are referring. Let me check. So here is not domain. Here is the latent space that they are characteristics of time series, not domain. So I don't. This. Oh, so okay. It's in the input space in the your training data, but in the shared latent variable. So it not mean that it's healthcare. Yeah, it's yeah. The color are confusing here. You think that this green matches this green. No. It's in Latin representation. You are separating like these these factors here. You are not separating the domains, but yes, I agree. The coloring is confusing here.
I remind my question. What, in your opinion, what can improve this kind of time series? For example, you have computing and another kind of things that influence this kind of time series. And we talking about in this week about mathematics and the statistics. This kind of things can improve this kind of time series.
It was here in the open problems. What can improve this time series? So, for example, have a measure for transferability. Then we defined what should be changed in the model that guarantee transferability, or here, what should be added in the model regarding the data. So it's open problem. We don't know if your question is that what mathematics can do. So far, we don't have. So the idea of presenting this was encouraging mathematicians and statisticians to work on the theory behind this, to before doing another experiment empirically, we can estimate if this change generate the expected results or no.
Any other question? So actually, I have a question. So you mentioned tokenization, and the fact that for LLMs, tokenization is kind of natural because the language is by nature amenable to tokenization. But so how is this done for time series? Like, is it done like in a straightforward way by discretization, discretizing over the space, or is there some smart way of doing that?
So it's an open problem because, as you said, tokenization in large language models is solved. You defines some words or piece of words as tokens. But the time series is, there is a research on this. You use one observation as a token, you use 16 observations because they are numbers. They don't have meanings like natural language. So it's research on this, how to implement proper tokenization. There isn't a clear answer on this. And they used, for example, this patch-based to solve this. They generate patch, or they use raw observations directly to the model. So we don't have the right answer. Which tokenization is the suitable ones? Different from natural language models that we have the answer. But in patching, so in patching, imagine you have a time series with 1,000 observations. You separate with groups of 50, 50, 50. Imagine they are non-overlapping patches, and use these patches to input the models separately. Like, imagine that they are like tokens. Piece of the observations, yes, as a patchet, and you don't need to implement a transformation. For example, in Chronos, they do. For tokenization, they do quantization to transfer the patches, then use the quantized information in the model. But you don't need necessarily do this. Only break your data set, your time series in different segments, and use in the transformer architecture those segments.
Okay, so thank you very much again. Thanks again, maybe in clap of hands. And so if there is no more question, we can have the coffee break and Então vai ser agora a última palestra do evento, pela Nina Hirata, que é professora aqui do IME no departamento de computação e que fez doutorado e tudo aqui no IME, e que vai falar sobre Beyond Brute Force, Inductive Bias in Deep Learning Models.
É esperado que eu fale em inglês, é isso, né? É que você falou em português. In English, okay.
Sorry, no, so yeah, let's do it again.
No, I can present myself.
Okay, got it. Okay.
Sorry, because I heard in Portuguese, so I thought, oh, maybe I can speak in Portuguese. I feel more comfortable, but it's okay. So, good morning, everybody. I would like to start thanking the organizers for inviting me. It's a great pleasure to be here. So I will start telling a little about me first. So I'm in the computer science department here. And I am at USP for some decades already. I will not tell you since when, but I did my undergrad and master and PhD here. And I am working with machine learning since my master, so some decades already. And in the last 10 years or so, I would say I am very much on deep learning. And I also would like to thank FAPESP, CNPq, MCTI for funding my projects, my students, and so on. So the idea today is to bring some math, I believe, in the deep learning context, which has a lot of engineering aspects too, but let's focus on the math. And my idea of the presentation today is to give the context. I believe in not all of you are very familiar with deep learning or neural networks, so I will give the context. I will not explain these models in detail because there is no time for that. But just say enough for you to understand what are these large models, what does it mean to train these models, and I think an important part is this thing called bias variance trade-off. Probably this is a kind of known concept, whatever, but I will talk about that. And more importantly, I think we have important challenges nowadays that we are reaching some wall in the sense that things will not scale. They are scaled already, so that's the problem. And that's where inductive bias may help in the training of these models. And the second part, which I suppose is the main part of my talk, is to kind of present three types or categorizations of inductive bias, and I will use some examples from the computer vision and signal processing fields to illustrate how we can use what I will call inductive bias, or everybody calls, and it's the idea. Talking about the context, first thing to understand is what is a neural network. I suppose everybody has an idea of what it is, but basically is this dense graph. In the left, you have the input data, then some layers, and at the right, you have the output layer. So in a sense, you can think that this is a box, a black box, as they say. You have inputs, you have some massive processing that will generate an output. So mathematically, this is just a mapping that takes a vector in the n-dimensional vector space and then generates the output in another dimension space. But essentially, each of the circle, the whatever, my vocabulary is not rich enough, is a simple function. It's just, in this case, just a linear combination of the inputs. So you can see the edges here, the Aresta's edges connections. So each this node or this unit will receive all the input, will perform a linear combination, and then usually you have some nonlinear function which we call activation function, which will take the result of the linear combination and transform into a single scalar. For instance, if you go past the combination to the sigmoid function, you will have the output in the 0-1 interval. And all these nodes will perform the same thing. So you will have outputs here, and this will feed the next layer, and so on. So if you now look at this as a box, it's just a mathematical function. And there are theoretical results showing that you can have networks that are can approximate continuous functions. I mean, I'm being kind of loose in this, but it's not here, I think. So now we are leaving the deep learning era. And what people call deep learning, they are just neural networks, but with multiple layers. And as you can see, different layers. So these architectures, they may have a different type of layers, type of nodes, blocks, connections, and so on. But in the end is you have the input in the left and the output at the end, and in the middle there is a composition of functions of different types. We can think this way. And what I turn here, I don't know, I think I have to face the public, but then I cannot see there. It's kind of complex. But it's okay. It's with that. So there's a massive number of parameters. What do we call param? Check the microphone. What do? Eu acho que não é só o. Eu acho que sim. Se eu viro para cá, se eu viro para cá, volta. So I have to do. Okay. Here? This way? Okay. Tá, okay. But I don't know, I will try. Okay. So, no. Doesn't work. Okay, let's go. So what happens with these deep learning or deep learning models is that they are neural networks with a massive number of parameters. What I call parameter is, as I showed here, all these connections have a weight, which is the coefficient when you compute the linear combination. And those coefficients are learned during the training of the network. So if you have this massive, large, huge network, you also have a massive number of parameters that need it from data. Okay? And just to give an idea of what I mean by massive number, everybody, I suppose you use or have used already ChatGPT. the initial version that was released, I think, in 2022, I don't know, was based on a transformer model, which is a deep neural network model called the GPT-3. And GPT-3 has 175 billion parameters, right? This is to give an idea of the scale of the things. So, networks, we need to accelerate here. We basically assume that an architecture is defining not working, which we will call hypothesis. That's this way? Ah, okay, thank you. So the problem was another one. We have a family of functions, hypothesis space, which is the, let's say, the set of functions that neural network architecture can implement. If you change the parameters, you will have different functions. What? It died again. What's happening? I don't know. Okay. We need training data to use this. Yeah, okay, I will try.
Sorry.
No problem.
It's not working.
Go to the
traditional.
yes, traditional one. Hello, hello. Okay. Now I have to decide how to. Okay. So we need also data. So we are supposing we have some training data. And what I mean by training data is input-output pairs of like X is the input, Y is the output. So I am supposing someone did this work of collecting input data and defining what would be the desired output, expected output for that input. And we also need to define a loss function, which is basically a function parameterized by the parameters of the model. And what it basically do is to measure the discrepancy between the output that is expected and what the model is predicting. And my goal in doing this training of the model is to have a good generalization of the model, which means I would like to find a hypothesis which is able to predict the right outcome for new sample, not those that are used for training the model. And all this process is basically done by minimizing the loss function. So you try to find the theta, the parameters that minimize the discrepancy, and then you have the parameters of the model. That's the basic idea. Now, what I think will lead us to discuss inductive bias is to first understand this trade-off that involves the hypothesis space, the amount of data you have, and the performance, I mean, how the model will behave out of sample or your data set. And here it looks very complex, but it's the idea is very simple. So what I call E out here is the error of the model out of sample or on new data, or if you wish, on the population and not on the sample, right? And E in is the in-sample error, the empirical error, the error on your sample or your data set. And omega here is what we call generalization error, which is basically the gap between what you are observing on your sample set and on the population. The thing is that you will never be able to compute this error on the population, so it's just a theoretical value. But if you try to estimate this from the error you are observing in your sample, you can reach this bound. This is a theoretical result. And this gap here, which we call generalization error, it will depend on the hypothesis space, which can be small or very large, simple or very complex. It will depend on the amount of data you have had to train the model. And the delta here is just a confidence you have in this bound here. So I think the important is to understand that this here, this is the trade-off in the sense that if you are using a simple model, that means that you may have a very large error even in your data because the model is too simple and it cannot fit the data. But on the other hand, your generalization error will be small, meaning that the error you observe in the the sample you have in your data set is very similar to the error you would observe on the real world. On the other hand, if you have a very complex, very expressive set of hypotheses, you will have small in-sample error. I mean, you can fit some model to your data. It will be perfect for the data you have, but eventually your generalization error could be very large because it has lots of degrees of freedom, so perhaps the model you chose is far from the real optimal one. That's the idea. So this is the trade-off. So in the end, what we want is to have models that, sorry, it's not, well, stop it. We want models that will have small populational error. And for that, we need to reduce this bound, right? So we would like to have small in-sample error. So my hypothesis space cannot be too limited. And I also want to reduce this generalization error. So I cannot have a too complex hypothesis space. So there is some trade-off here. And the issue is how to use this modeling to, and then use inductive bias to reach good models that reduce the real error. So just to mention the term people use, there is underfitting, meaning that your hypothesis space is too simple that it's unable to capture the patterns or whatever, the relationship between input and output. And overfitting is the contrary. Your model is too expressive that the choice you did, it fitted very well on your training data, but there is no guarantee that it will work well for new data. So this is a trade-off. Now, what we can, what deep learning models are doing or why they reached this success level performance. See the language models that are perhaps smarter than us. For some things, yes. Not for everything, of course, but what they did is first very large models, large hypothesis space. That means that obviously you can fit any training data, or that's the idea. And to keep control of the generalization error, massive volume of data. So language models, basically, they were trained using all the data available on internet, right? And also massive computational power to process this volume of data and the computation needed to train these large-scale models. So nowadays we are facing real challenges. And one that everybody, I think, already read or heard around is the issue of energy consumption. So large companies are building, I don't know, the usinas elétricas or whatever, to generate energy to feed their data processing centers. I think there are some problems of economic nature, like only large companies can train these large models, so there is some imbalance of power in this sense. But I will not touch this anymore in this talk. Let's focus on, also there is this third thing that is, we are reaching the wall in terms of availability of data generated by humans. What I mean by that? Nowadays, there are a lot of data that is being generated by AI. So if you train a machine learning model using AI-generated data, you're basically doing kind of inbreeding. So there are some studies that is already pointing in the direction that this, if you keep training the model from the data generated by them, they will degenerate eventually. The quality will decrease. So the motivation of the talk, I'm spending too much time talking about this, but the idea is how do we face these challenges, or more specifically, this issue of a scale. So we don't have computers to process large models, or we don't have a large volume of data if we are focusing on specific problems. And so what we do, the question we want to answer is this: can we scale down the process? Meaning use smaller models, use less data, and therefore less computing resources, and yet have good performance. That's our goal. So here is where inductive bias can help. And the definition of inductive bias basically is any assumption that the algorithm uses to generalize beyond training data. If we do some parallel with how our brain works, I think, you can say that when we see or we observe something, we know usually what is happening because we have some context, we have a background, we have some bias, right? So, but if you don't have that, you can see something and you won't be able to understand or have an interpretation of what's the meaning or what's happening. For the machine learning models, the same happens in the sense that if the training basically is based on data, and if you don't provide anything else, all it can infer is based on the data. But we know that those data come from some context. They have some structure, some whatever context. And if you can integrate that knowledge into the model, then the model can use that information to do the prediction. That's the idea. So when we talk about the inductive bias, is how we can include that in the model itself, those priors or bias that we might have about the world we are, or the domain we are processing. And in this sense is that this inductive bias will kind of help to fill the gap that the data alone cannot fill. And in doing so, we would like to keep the in-sample error small, to keep that bound small, and at the same time also control the generalization error. So now I will start to organize these inductive bias approaches in 3 categories. If we look in the literature, we have lots of methods, techniques, and sometimes it is not clear if they are just random hacks, engineering hacks, or if they have some meaning in this more statistical sense. So that's the point. So I divided the types of bias that we can use in 3 types here. So structural, and this means understand the structure of the data, perhaps properties that the data carry, and what are the mappings or functions that preserve that structure. And that this kind of knowledge can be included in the architecture of the model, of the network. So in a sense, this is kind of limiting where the models can go. In other words, I am limiting the hypothesis space, but not arbitrarily, taking into consideration the nature of the data. That's the idea, right? The second group is representation priors, meaning that now we are looking into the space of representations, and let me explain what I mean by representation. In the neural network, in the input, you have some representation of the some data. For instance, if you are thinking on images, you have a matrix with some values. And as the network processes layer by layer this data, you are changing its representation. And we have then what people call a latent space or embedding space or representation space or whatever, which is how the input data has been transformed to generate another landscape of representations. And people often observe that these representations, they live in a small subspace or some specific manifolds in the large dimensional space. So here the idea is to explore the geometry of the manifold. If you have some knowledge of which manifold is more appropriate to process some kind of a property of the data or whatever, you can kind of force your model to take the input and put on that manifold. That's the idea. So you can measure whatever in that manifold and not in the general Euclidean space where similarities kind of get lost when dimension is very large. And then the third type of bias is navigation, in the sense that here I defined where models can go. Here is kind of saying which place is the good place in the latent space. And this third prior is how we help the model to go to this good place. That's the idea. I'm getting tired of speaking English. My English is starting to broke here. Sorry. So now I will present examples for each of these three categories, so you will have a better sense of what I am talking about, I hope. And for the structural case, I will use images as example, right? So for that I will need to, let's think the following. Suppose my task is to, these are handwritten digit images. They are just matrix, 28 by 28. White means 1, black is 0, so it's a binary image, or perhaps grayscale. There are some gray. Anyway, the idea is to, the input would be these images, and I would like to just say which is the number from 0 to 9. So we will have, if we think on neural networks, we could just consider each point of this matrix, each pixel, 784 pixels as the input of the neural network, and 10 outputs in the 10 nodes in the output to say if which is the digit. But if we do this, what will happen? We will lose totally the information of the relationship between pixels here, neighborhood adjacent information. Another thing that will happen is that here the digits are kind of centralized in the image, but if you have the image on one corner or on another corner, it can be the same shape. The neural network will have to learn the same digit on several positions of the image. And that doesn't make sense. Obviously, I will have a large number of parameters because this is just a very small image. And if you have a 100 by 100 image, you have much more nodes and much more parameters. So for images, people came up with what is called the convolutional neural network, and it is based on the convolution operation operator, which was created in the field of signal processing. Here I will just give an idea of what is convolution when we are working on images. So this is the input image. The convolution will take the input image, a small function, a function with a small support, which is the K here, kernel. And the idea is just to slide this kernel over the image and compute a dot product, a pointwise product. Then you sum up, and then you will have the result. So here you can see that if the kernel is in this white region, you have 8 plus times the white one, whatever, minus 8 plus 1, so 8 minus 8 is 0. That's why it is 0 here, black. And when there is contrast, you will have some differences, and that's why you see the edges or contours of the object here. So this is a kernel or mask or whatever, they use different names, that can be used to transform the image and emphasize some feature or whatever. You can blur the image just applying the mean here instead of this mask, and so on. So this was very much used in image processing. Then now they incorporated that in the deep learning model. So here is a neural network, and the first layers are convolutions. And they figure out how to compute this efficiently or whatever. But the key point here is that the mask of the kernel used to perform the convolution is also trained. It's learned during the training of the network. So we no longer need to design the kernel and generate the output. The model itself will learn the kernels. And in some sense, people call this feature extraction part of the model, because here is just a sequence of convolutions and what people call pooling layers, which will reduce the size of the image gradually. And there are explanations why this makes sense, but it's not for today. It's another talk. And once you have the final small image here, you can flatten it and feed a standard neural network. And this part will use these features or variables that somehow describe the input image and perform the classification. That's the idea. So now, why convolution is interesting, or which is the property we are trying to use from the input data, is the following. For instance, that example of the position of the digit I mentioned. If the digit is on this corner or other corner, for the neural network, it makes a difference, but for the convolutional network, it doesn't make a difference because the kernel will slide and it will see the same pattern here or here. So in this sense, you are learning to recognize patterns, and it is not tied to the specific position of where the pattern is appearing in the image, right? Because you are just using the same kernel to scan all the image. So as a consequence, what happens is that convolutional layers satisfy this shift equivalent property, meaning that if you take an image X and you perform translation and you apply the convolution, it's the same as, oh, sorry, wrong button. It's the same as first applying the convolution and then doing the translation. Then there is another property which is shift invariance, and this is not totally true because of the pooling. Something started to break, and I will not enter into detail. If someone is interested, I can explain later because I think it's not so simple to explain very quickly because I don't have the vocabulary. But in general, when we look at the whole network, what happens is that we can say that it is approximately shift invariant in the sense that it keeps this property of not taking into consideration where the pattern occurs in the image. So it learns that a dog is a dog if the dog is here or there. Basically, that's the idea. And when we compare this network with the conventional neural network, what is happening is that now we are preserving the spatial relationship between the pixels. We don't lose this information. We use the same kernel all over the image, so we are sharing the same weights on the entire image. That means that we have fewer parameters, and all the result of all this is this shift invariance property, that the position of the pattern is not does not affect the result, which is not true for neural networks, the conventional ones. So this is one example, just to to show how you can take the properties or characteristics of your data and put that in your model. Another bias of structural nature, this is purely mathematical, is, for instance, it's a very simple one. Suppose I use a kernel of size 7 by 7 to process an image. So for the disposition, I will have this result. But I can break this kernel into a sequence of 3 by 3 convolutions. What I mean is, if you take this 3 by 3, apply a 3 by 3 convolution, you have this point here. But each of these yellow points, they use the information from this orange region, and each point here from this blue region. So applying a 7 by 7 kernel on the input image is somehow is not equivalent theoretically, but in terms of which part of the image the model is looking is similar when you apply a sequence of 3 by 3 kernel. So the advantage of doing this way is that you are reducing the number of parameters. And so you are kind of reducing the complexity of your hypothesis space, which means maybe I will need less data to train when used this way and not this way. Okay, now we go to the second type of bias, and this is has to do with using geometry, and we will use EEG signals for that. Okay, let's explain this one. I don't know if you're aware of these people that put some sensors on your head and try to read what is in your mind. Here is an example using EEG, which are these sensors that will measure, I don't know exactly what, but it's the brain, the neurons activity in your brain. And it will generate, let me advance, it will generate this a set of signals. So each signal corresponds to one sensor in your head here. So in the end, I have a signal with this dimension, C channels. Okay, I have C channels and some time steps here. And what people found out, I don't know, along the time is that to capture the correlation between these signals, covariance matrices are very good for that. And if you put this signal in the Euclidean space, you kind of lose this correlation or synchronization information. So people work with the covariance matrix. I don't know, yes, here. This is the covariance matrix of this signal. And then the idea is now to work on these matrices, which have a nice property. They are symmetrically positive definite, and it generates, they live in a manifold, a nice manifold. I don't know much about math. I'm not expert in math, but the idea is that this type of matrix, they form a nice manifold, whatever, and you can apply transformations in this space. You take positive matrix here, apply this BMAP transformations, which I don't know what is, but it's basically some transformation of this type. The only constraint is that W matrix must have orthonormal holes. I think this is enough, sufficient to guarantee that when you compute this transformation, this new matrix will still be in the manifold. So here we can think, make a parallel to convolutions. You take an image, you apply convolution, you have another image. Here you apply this BMAP, you have a SPD, you apply the BMAP, you will have an SPD. That's the thing. And then what's happening is next, what you can do is take this some point here and project it to the plane that is tangent to the identity matrix, as far as I understood. I don't know what is this. I think log Hague do this. This is some activation type of processing. It's not important here, I think, to understand the idea. But what I want to illustrate with this is that idea of, you know, that kind of signal, they have some nice properties if you keep the representation as a covariance matrix. So you will work on that manifold. And you can do the optimization or training or enhance its representation on that manifold. And then only at the end of the process, you can bring it back perhaps to the Euclidean space to do just the separation to do the classification. That's the main idea. And here is just an implementation of the network here. It's the same idea. Here is the signal, X, and then here they apply some convolution. I think it's to filter noise or improve the signal somehow, and it's trained. This is the covariance matrix, and then you can implement multiple layers that involve the BMAP and the Hague here. So here, making the parallel with convolutional neural networks, you can think of like a convolution layer followed by an activation layer, a nonlinear activation. And you can do a lot of that. And then finally you map the data to the Euclidean space and do the classification there. That's the idea of the network. So all the learning or enhancing the representation was done on the SPD manifold. Okay, so the last one, okay, this is more simple, is how to help in navigation. I have two examples. I think most of you know regularization, R2 regularization. Basically, in this case, what we do is the theta are the parameters. This is the loss function. And we added a new term here, which is the norm of the weight vector. And the idea here is to penalize weights or parameters that have large magnitude. And why? Because what I would like is to have models that are robust. If you have large weight, if you change the input a little bit, it may amplify the change in the input, and the output may have a huge difference compared to the small change in the input. But if you don't have large weights, small changes in the input will generate small changes in the output, which probably is what happens in real life, in the sense that small changes will not change the response. And therefore, by doing this, we have models that are more robust to, for instance, noise in the input. Okay. this one, I think I will confess I used the AI to generate it. Not the slide, but the ideas that is here. Because I needed a simple one to put. And I didn't know this can be seen as navigation prior. But, and then, I don't know how many of you know what is gradient descent, but it's just an optimization technique, because we are trying to find the minimum of a function, so we can take the parameter that we have now, parameter values, compute the gradient, and update these parameters to the direction where the negative of the gradient, because the gradient is pointed to the direction where the function is growing fastest. So the negative is where the function is decreasing. We think so. So by doing that, after updating the parameters, you hopefully will be in a place where the loss function has a smaller value. And the idea is to repeat that to get to the minimum of the loss function. And stochastic means that you don't use the whole set of images to I mean the input data to compute the loss function, but you use one or a small batch of data. And therefore, when you do this update, you're not basing your update on the whole set of data, just a partial part of the data. So this update is kind of noise. But it seems this works as a kind of regularization, because this way of updating the weight will make the parameters move kind of not in an optimal way in that moment. It will maybe go this way, then, and it becomes more robust to small local minima, for instance, because you are not considering that the whole data, you're using part, so there is chance that you will escape that local minima and go to a better place, for instance. I don't know, this is the explanation. It's kind of, I should have some figure to show, but another thing that I didn't know, I am believing in AI. They say that this stochastic gradient descent, they tend to grow the local minima, and it makes the model more robust. Okay, so these are some ways to help the model find the way to the best place in terms of loss. And I suppose there are other priors or bias we can use, but these are the examples I brought to today. And this is the last slide. So in the end, I think the key message is that, well, as I said in the beginning, we are reaching the limit in terms of scale. Too many computing power needed to run these models, many data, large models, and so on. So I think the natural way to escape this is to build smaller, more affordable models. But we want them to be good enough to be useful to our problem. So this is where you can use your bias about your domain, your data, your application, whatever, and try to put it in your modeling. So inductive bias is basically that. What you know about your problem, your whatever, so you can put the information on the architecture. So somehow you are restricting the hypothesis space, reducing number of parameters. That means you will need less data to have small generalization error. And the trick here is to include constraints that are coherent, consistent with your your problem, right? You cannot put arbitrary restrictions. The second is representation prior, in the sense that if you know that your data behave better in some manifold, you can try to work on that manifold or subspace, whatever. And navigation is just how do you make the computation, the parameters go to the right place. That's it. Thank you. Sorry, I'm kind of tired because I had classes at 8, so I'm kind of talking for hours continuously.
So, is there any question?
For implementing our view about inductive bias, you need a whole team, no? Because you have some kind of things that you have people specialize in kind of things that you mentioned.
I don't know if I understood correctly. Can you
Ok. A sua ideia sobre a inductive bias, eu penso que para você conseguir fazer essa implementação, você precisa ter um time bem especializado, né? Porque as características que você está colocando para esse modelo, elas requerem muita técnica, né? É isso. Isso. Isso, é para...
So the question is to implement this bias in whatever, in the pipeline, processing pipeline, you will need, I mean, programmers, people that can code, and yes, there is no other way, which is different from coming up with ideas of bias that you can use, but your question, I think, is how you put in your architecture or loss function or whatever. You have to program, and well, there is no other way. But many of these biases are already implemented in the libraries, PyTorch or whatever. So depending on the, for instance, regularization, when you added some term on the loss function, I think that is pretty easy to adapt to the code that is already available. But if you want to create whatever, a new, I don't know, I think people already did, but for instance, images, you can take images and map them to the frequency domain and work with Fourier, whatever, signals. I think someone already did that, but suppose nobody did, you would have to program that kind of layers and do that. But or hope someone will do that. For instance, this SPD one, someone already did the layers, so you just need to take the layers and build the architecture, basically stacking layer after layer. I hope I answered your question. So I would say that to make these things work, it's not one person that will do. It's multidisciplinary. We need the programmers, we need whatever people that can not only program but make things work on, you know, these distributed processing environments, because these models are huge. So you may have the code, but you're not able to fit the model in one GPU. So you have to make the computation in a distributed way that requires another skill in programming. I don't know how to do distributed processing. I never did that. I have no experience with that. But these libraries are, at some degree, prepared to do that already. So I don't know how many effort is needed to create new things.
In general, when we talk about neural networks, we always see ways of optimizing over the parameters, but I think the precise structure of the network has a great impact in the performance, right? So and people try different architectures and different. Do you know methods to try to select this architecture in some automatic way, or there are things to do to optimize this selection of the architecture?
So the design of the architecture, I think, at a great extent, it's just engineering work. I suppose many people try. They say, oh, what happens if I change this layer for another one, or if I place one module here, or I change this kernel for another one, or whatever. And some of these changes will survive, in the sense that will survive the practical test. I don't know, there is a term for that, I think. Others will die, and nobody will ever know that someone attempted that, perhaps. But I think many of the architectures we have now, they are based on the knowledge people had already from the past. For instance, images. Using convolution is something that, or signal processing, everybody did it since, I don't know, centuries ago, perhaps. So here the idea is just how to include that knowledge into the architecture. You have the convolutional neural network. And convolutional neural network, they exist since the 90s. The problem is that nobody was able to train the model because we did not have data enough to train the model. Or when we think about, for instance, time series, your data is, I think it's Markov chain, whatever. You have the dependence on the past. I mean, your future data will have to take into consideration what happened in the past. For that, we will have the recurrent neural network, which somehow will accumulate the data it's processing in sequence, and then use that to update the state and generate the next prediction, for instance. What else? What kind of another architecture, yes. But in the end, they are all graphs, in the sense of you have neurons, nodes that process data, and connections between them. And usually data will flow from one side to another. Eventually, yeah, basically that. And we have also neural networks that work on graphs. which are an image is a particular case of graph, so you don't need to represent each pixel as a node of a graph. But if you have some non-rigid structure, like a protein, you have the molecules, and they can connect in a different way. You can have graphs to represent that, or social networks. You have people, and the connection between these people, among these people, may vary. It's not regular, so you can use graph to represent that, and then you can process or have neural networks that process graphs. So it's whatever an idea that you have, you can try to apply this idea of trying to learn the representation, attain the best representation.
Another one. Do you think to use a genetic algorithm in your plane, in your view? Yes.
I didn't work with that so far, but I had a student that worked in the past with genetic networks. I don't know. I don't think, but I know that there are. I think Florencia was talking about the design of the architectures. I'm not sure how it is nowadays, but for some time there was some effort to develop methods to find good architectures. It was called the NAS, Neural Architecture Search. And I think they used, for instance, genetic approaches. But I don't know. I think that died. Do you know, Ahmed? Do people use that nowadays? I have no idea, but there were some years ago that was very hyping, like many people was interested, but nowadays I think the interest diminished because the network this method generates is hard to understand, I think, because basically what it does is it has some blocks, processing blocks, and then try different connections or assemble different architectures connecting these models, and eventually one will perform very nicely. But when you look at the architecture, it's just a random combination of things, and it doesn't carry any logical meaning. Probably, I don't know, I have no experience with that, so, but that's what I can imagine. Right. Okay. Thank you.
No other question? Okay, so thank you very much. Let's thanks again. So, okay, this was the last talk. So, in the afternoon we have some in-city meeting, but I'm not sure what it's all about.
No, so some groups will be working here.
Okay.
The groups that are working together.
And well, there is a working session, which I guess means that you can just stay here and use the blackboard and feel at home. And but yeah.
There are some groups that are collaborating. Be free to work on what you work.
So it's free time.